Footsteps of Giants chronicles 25 years of America's adventure in space, from Alan B. Shepard's historic flight in 1961 to the Space Shuttle Challenger's tragic explosion in 1986. This program features dramatic new footage that lets you experience firsthand the tremendous accomplishments of the space program. The power of a rocket is the key to man's ability to penetrate the mysterious vacuum of space. We could start our story with Chinese rockets and recall even earlier fantasies. But we need only go back to the German V-2 rocket of World War II when fiction began to focus into possible reality. From a program with some spectacular failures, the engineers learned how to build a working ballistic missile. It was the forerunner of the satellite launchers, such as this American one based on the Thor missile. Rockets have to climb up from the ground and turn over into the right orbital path. To do this, our limited technology forces us to build the rocket in stages. Earlier stages are discarded when they've used their propellant. The interstage fairings are discarded, and the rockets of the final stage accelerate the payload it carries. Keep the rockets burning, and we can send probes to explore the depths of the universe. The space era began dramatically on October 4th, 1957, in the Soviet Union with the launching of the first satellite, Sputnik, into orbit. The world listened with amazement to the signals received on Earth as the satellite circled the globe. America followed the Soviet lead by putting a small spacecraft into orbit in 1958. A startled world then learned that a dog, Laika, had been put into orbit by the Soviet Union to measure the effects of weightlessness. The United States scientists conducted tests on Earth to check the effect of spaceflight on a human being. The first real orbital conditions were to be tested with a monkey. The USA then developed a Scout solid propellant rocket to launch small payloads from mainland sites and offshore platforms. Another successful American rocket, the Thor Delta. Extensive testing of high-performance rockets is very important. In the 60s, Britain led Europe with Blue Streak, a large and successful rocket. The structure was thermally tested. The thin wall tanks, which would carry the propellants, were pressure tested. This simulated launch checked the release mechanism. Using this experience, Britain successfully developed Black Arrow, its own national launching rocket, and put up a spacecraft into orbit in 1971. In order to launch a man in space, more powerful and reliable rockets were needed. The Soviets were in the lead position and launched the first man in space, Yuri Gagarin. The massive Vostok launcher prepared for its historic liftoff. Gagarin instantly became a hero in the Soviet Union. Working at a frenzied pace, the United States was able to launch John Glenn nearly a year later in a Mercury capsule. The power of the Soviet launchers allowed dramatic progress, and 2 men were able to fly on the Voshchod manned capsule. For the first time, a man, cosmonaut Leonov, left the safety of the capsule in a pressure suit and maneuvered in the hard vacuum of space. America countered with the 2-man Gemini capsule. Astronauts maneuvered outside the capsule, this time with the added innovation of a simple but effective handheld propulsion system. It was now possible to think seriously of exploring the moon. The American Lunar Orbiter spacecraft provided the first clear images of its other side, never seen by mankind, and so built up a comprehensive picture of our closest heavenly body. The American Surveyor spacecraft achieved an historic first by landing on the moon and transmitting information on soil characteristics. The Venera space probe was the Soviet answer, duly dispatched to Venus, our nearest planet. After several unsuccessful missions, its hostile, hot, and dense atmosphere was finally penetrated. The probe survived its landing and sent back these primitive but historic images. America targeted Mars and developed the Viking space probe. The orbiter part circled the planet, and the lander descended by parachute, then by rocket, down to the surface. The images from orbiter revealed the surface characteristics, including the dried-up riverbeds. All the water is now concentrated on the polar ice caps. Meanwhile, the lander extended its scoop and analyzed soil. It also transmitted dramatic pictures of the surface and the irregular-shaped moon of Mars from its television cameras. The Soviet Union was ready to look more closely at the moon with its extraordinary vehicle, Lunarkod, remotely controlled from Earth. After descending from the carrier rocket, it covered several miles of the surface. America reached deeper into the solar system. The Pioneer space probe flew past Jupiter with its swirling red fluid surface. It photographed one of the many moons of Jupiter, Io, with its volcanic eruptions, as well as dramatic pictures of its other moons. The signals carrying these pictures took 45 minutes to reach Earth and were so weak that they had to be received by enormous aerials. The space probe continued past Saturn with its incredible pattern of rings. Saturn was chosen as the name for the massive rocket built to carry man to the moon. This is the transporter, taking it from the assembly building to the launch pad. This early test reveals the power and size of the rocket. Extensive research was carried out, including this one-man rocket pack, as well as simulated motion in 1/6 gravity. Ejection tests were carried out on the command module. Splashdown in the water was checked. Would it right itself? Could the men get out safely from the hatches? Finally, 3 men climbed into the command module for the liftoff of Apollo 8, Christmas 1968. Approaching the moon now with increasing clarity, and finally in orbit around the moon with the first view of its pocked crater surface. A weightless Frank Borman looks back at Earth, seen above the lunar landscape for the first time. One more dress rehearsal. This time the lunar lander moving down and orbiting the moon, but not yet landing. The stage was set. Neil Armstrong, Buzz Aldrin, and Mike Collins, the first crew to land on the moon in Apollo 11.
Neil Armstrong just reported back. It's been a real smooth countdown. We passed the 50-second mark. Power transfer is complete.
The press of the world was poised for the liftoff. Apollo 11 began its attempt to reach the moon. First stage separation, successful. Second stage, successful. Earth receding behind them, moon the target, coming closer into their sights.
Altitude 4200. Houston, you're a go for landing, over.
Then final descent towards the surface, feet away,
30 seconds.
touching down, dust rising.
Contact light. Tranquility Base here. The Eagle has landed. That's one small step for man, one giant leap for mankind.
Etched forever in our minds, the first photographs of astronauts on the surface, the first ghostly images on our televisions. Ascent module liftoff and rendezvous with the command module, tense moments closing in and lining up for the final docking. The happy and relieved crew tidied up for their return to Earth. They were destined to spend 2 weeks in this quarantine area in case bacteria harmful to Earth might be brought back. The final re-entry phase. The deployment of parachutes, the splashdown, and the recovery of the astronauts onto the carrier. And so, into the quarantine van, with 2 weeks to go before the ticker tape parade along the streets of New York. Apollo 12 followed to another part of the moon. But Apollo 13 suffered a dramatic explosion in the service module during its outward path. The world held its breath for 3 days. Carriers waited, hoping for a successful return. The space experts worked desperately with the crew to keep them alive. Committed to orbit the moon, the spacecraft succeeded and returned victorious to Earth. Apollo 15 carried a new piece of equipment, a vehicle called Rover. Rover, driving across the surface, widened the area of research considerably.
Bob, I've trenched across the trend of the yellow by the orange. There is light gray material on either side. Oh man, that's incredible. Say, Gene, we're going to have to...
Collecting samples from the surface was not always easy, and there were some tricky moments.
Okay. Stay there.
Help is needed getting up, a little like a tortoise on its back on Earth. Hundreds of pounds of lunar soils and rock brought back to Earth were part of the rewards of this highly successful Apollo project. In the mid-1970s, the Soviets and Americans joined forces in the historic Apollo-Soyuz test program. The Soviet Soyuz and American Apollo manned spacecraft linked up using a special adapter so that the 3 American astronauts and the 2 Soviet cosmonauts could meet within an international space station for the first time. Rendezvous and docking is a difficult operation. They require completely opposite control motions to those instincts suggested by man's earthbound experience. Paralleling the developments in manned spacecraft is the building of communication satellites. What powers a satellite? Electricity comes from panels of solar cells. A lightweight structure contains all the housekeeping and payload equipment. An early European satellite, SRO-2, had its solar cells mounted on its cylindrical body. Since spacecraft operate where there is no air, gravity, or weather, they can come in all sorts of shapes and sizes, like this family of European communication satellites. These satellites generally work in the high geostationary 22,000-mile orbit around the equator, which appears stationary from Earth, compared with lower orbits which track across the surface. Because these lower orbit satellites move relative to the ground, they need to be tracked by aerials such as the 30-meter dish at Gunhilly in England.
Captain Booth looking anxious.
consciously at the quality. Delicate tuning to hold the toppling picture. There it is.
Some aerials are protected by domes. Early American ones were very large horns.
Captain Booth still looking wise.
Small tracking aerials can be made mobile. An earlier communication experiment involved bouncing signals off a band of 250 million hair-like needles put into a 1,000-mile orbit above the Earth. This was followed by a similar experiment with the Echo balloon, 100 feet diameter, made of metallized plastic and inflated to its spherical shape once in orbit. Of course, real progress came with the later, more powerful active communication satellites such as ATS-6. Its 32-foot diameter aerial provided a strong signal to send TV pictures for educational purposes to 2,400 villages in India. The early bird communication satellite in geostationary Earth orbit enabled television pictures to be transmitted between distant points on the globe. By necessity, satellites are becoming larger. Intelsat, supported by over 100 countries, started with Intelsat 3. With 1,200 telephone circuits and TV channels, they were built with ever-increasing size and capacity. Ground stations of different sizes were built to work with the satellites. Some were small, but the very large 100-foot dishes pointed at different satellites are still required. Direct broadcasting into individual homes via satellite, taking programs directly from the studio, became possible with the increased power of satellites. Communication satellites serve a wide range of civil and defense purposes, including search and rescue for ships and aircraft, saving hundreds of lives. The Earth can be observed from the high platform a satellite provides. Early Tyros and Nimbus satellites had sensors on board for meteorological observation of the changing cloud patterns by day and by night. False color images of the Earth identify its vegetation, mineral resources, and heat. Hurricanes can be observed. Life and property can be saved with early warnings of their path of destruction. Swirling cloud patterns over Europe can be seen clearly when speeded up. The information obtained is collated and distributed to many countries. In 1972, a major advance was achieved by the American Landsat Earth observation satellite, which circled the globe in polar orbit, taking images of the world beneath. Farming communities benefit from this information. Other areas reveal their secrets. Death Valley, Manhattan, and Denmark. Marine applications are very important, as demonstrated dramatically by CSAT, launched by America in 1978. In the 100 days of its operation, the marine information obtained was valuable to offshore platforms as well as shipping. The data which comes from all these satellites will enable us to detect where fires are breaking out and help protect wildlife and forests. Early warning of weather conditions is of immense help to aircraft. New satellite systems will ensure that routine data is built up and made available using advanced analytical techniques. This analysis of the state of the ionosphere reveals how events on Earth disturb it. Microgravity is important, and biosatellites have been sent up to examine, in weightless conditions, the changed behavior of cell structure. OGO, the Orbiting Geophysical Observatory, opens up in space, and OSO, the Orbiting Solar Observatory, studied our sun. This is the diversity of scientific research in space. We cannot do these exciting things in space without the rockets to get there, as demonstrated so well by the Soviet Union. Private enterprise is now developing a new generation of launching rockets. Their commercial prospects are excellent. A private British design of a small launcher is well advanced, and an American company is now building Conestoga, seen here in an early suborbital test. Another design is Jarvis, proposed by the Hughes Company as a high-lift booster for the future. Small satellite mechanisms have to be opened out in orbit. Large satellite antennas have to be erected. But in the end, it depends on being able to get there. The increasing size of the satellites has led America to extend capability with this massive Titan rocket. Its two solid boosters separate. It can carry as many as 8 small satellites for ejection into orbit. These were the Vela nuclear detection satellites. This Soviet Union team is observing the preparation of the new massive Inertia rocket. This will put major space stations and other equipment into orbit. The first successful launch was in May 1987. The European Space Agency, the ESA, with its member nations, is designing a larger launcher to extend its capabilities, Ariane 5. It will be particularly suitable to carry the space plane Hermes into orbit with its crew and cargo. Upon safe return to Earth, it lands horizontally. Europe is now a prime supplier of launch services to the world. This is a simulated launch to enable the ground crew to check out what the real thing will be like. Hermes will be an important addition to the European space capability. America's early tests of aerodynamic vehicles led to the successful design and development of the space transportation system, the shuttle. In early tests and for transportation, the shuttle is carried on top of a 747. Here, it is undergoing an aerodynamic proving flight prior to the first launch into orbit. Rolling over onto the proper heading, the crew gets a clear view of the Earth and is more comfortable with the G-loading and the climb. After just over 2 minutes, the big solid boosters burn out and separate. The orbiter continues to burn its engines using propellants from the big external tank. This is later jettisoned, leaving the shuttle in orbit. Shuttle-launched satellites have their own rockets to go to higher orbit. The shuttle has carried up and tested the first manned maneuvering unit. This one-man spacecraft enables the crew to go outside and work. Without a maneuvering unit, but using life support packs on their back, the crew has recovered spacecraft such as Solar Max from orbit, brought it into the payload bay, and repaired it with the aid of the big robot arm. Dramatically, astronauts have gone out and recovered other satellites. This is the Palapa satellite, which failed to ignite its own rocket and has not driven into high orbit. The device the astronaut holds links up to the rocket motor nozzle. He draws the spacecraft back into the payload bay to bring to Earth. On Earth, these satellites weigh several tons, but in the weightlessness of space, the astronauts can move them and hold them with one finger. An astronaut flying solo. The large format camera carried in the shuttle took this high-definition picture of Holland. Unfortunately, not every flight is successful. The Challenger in January of 1986 was on a routine mission with a normal liftoff. 2 minutes into the flight, a fault in one of the joints of the massive boosters leaked a flame which led to the explosion and destruction of the whole vehicle and its crew. Into the future, fully reusable space planes, Sanger from Germany, NASP from America. HOTAL is a unique British proposal for a horizontal takeoff and landing vehicle. It uses oxygen in the atmosphere as a propellant on the way up and lands on a runway like an aircraft. These reusables will not be available until the turn of the century. Developments are beginning to keep pace with movies like Star Wars. Active, directed energy weapons are being designed for battle stations in orbit to destroy spacecraft and ballistic missiles, if need be. These would be launched possibly on multi-stage rockets and, when in orbit, aligned prior to deploying their weapon. Some might even be designed to collide with and destroy other craft. The main effort at this time is toward the development of very high-energy active systems. Lasers or directed energy would burn up and destroy enemy aircraft. Anti-ballistic missile tests involving the collision of one body with another with dramatic effect have already occurred. Another form of kinetic energy weapon system is deployed out of a shuttle payload bay. It remains in space until needed to intercept a ballistic missile. Railguns fire large numbers of pellets at hypersonic speed moving forward in a shower towards incoming targets, eroding and destroying them most effectively. Ground-based arrays of directed energy weapons might be used to destroy rockets or satellites. Possibly more effective, such beams might be reflected by mirrors in space, directing the energy towards the target. The ability to do this has been demonstrated most effectively. Among the more peaceful uses of space, the large Hubble telescope, already built, waits to be delivered into orbit. The scope of scientific research is limitless. Jupiter needs to be revisited. There is so much more to learn about the planet and its many moons. A spacecraft has already flown past Saturn. We need to visit it again to examine the incredible rings and other features which have been revealed. The hottest gases ever measured by man, a kinetic temperature of 1 million degrees Kelvin, have been measured above Saturn. A space probe has flown by Uranus. One of its most interesting moons is Miranda, seen here on the right, 300 miles in diameter, with cliffs 10 miles high. Our regular visitor, Halley's Comet, passed Earth again in 1986, and an armada of spacecraft was launched to intercept it. Giotto performed the most dramatic function, moving through the comet's inner atmosphere and surviving. Probes have traveled to Venus. Additional spacecraft have been sent to research our sun, crucial to our life on Earth. We may harness the sun in the next century, converting its light by solar cells to electricity. Beaming it to Earth by microwave, we could meet the growing demands of our world community. Phobos is designed to take even better pictures of Mars than these. Lunar colonies for research and material recovery are at quite an advanced stage of planning and could be created within 20 years. New material and technologies emerge from projects. New control and propulsion techniques enable us to build better and more versatile aircraft for use in our atmosphere. It is inevitable that we use our fourth domain, more satellites will be launched, providing ever-increasing services. Research will be carried out within the shuttle and the space station. Teleoperated orbital maneuvering vehicles will be developed from the shuttle to help retrieve satellites. The presence of men and women will be vital. Leaving the spacecraft to repair, recover, or build structures. The machine in the shuttle bay will enable the astronauts to build a light and strong beam, typical of the miles of such structures required in the bigger space stations of the future. Our research in space shows we can make pure drugs and other pharmaceutical products, grow perfect crystals for optical and electronic purposes, and make new materials. The large space stations being planned will enable us to take full advantage of these research techniques. The new products evolved will prove invaluable to us all. This is probably how the big International Space Station of the 90s will look, with contributions from Europe, Japan, America, and Canada. Space has so much to offer, to teach and help us. To cross its frontiers presents man with his most exciting challenge. Beyond, new horizons will appear.